Accelerators. Today in this presentation, I'm going to discuss a new topic, particle accelerators. In the beginning, the first chapter of Unit 2, we have discussed an experiment which is very important in nuclear physics. It's nothing but Rutherford alpha scattering experiment. In Rutherford alpha scattering experiment, fast moving alpha particles are made to incident on the gold foil. The fast moving alpha particles are made to interact with the gold atoms, and the result of the experiment led to the discovery of nucleus. Here, the alpha particles are made to approach the gold foil with very high kinetic energy. That means fast moving alpha particles are made to bombard the gold foil. Okay? And also, in Unit 3, you have a chapter, nuclear reactions, in which we are going to discuss that by bombarding nuclei with high energetic particles and analyzing the products, nuclear properties and nuclear transformations can be studied. That we are going to discuss in the nuclear reactions chapter. In that chapter, we are going to discuss the interaction between nucleus and the particles. Here, high energetic particles are required. These high energetic particles are made to bombard with the nucleus, and by analyzing the products, we are going to get information about nuclear properties and nuclear transformation. These high energy particles are also called as projectiles, and the nuclei is called as a target. Therefore, in nuclear reactions, the projectiles are made to hit the target, and as products, we are going to get residual nucleus and other particles which are so called as ejectiles. And in nuclear interactions, the commonly used projectiles, high energy particles, are nothing but neutron, proton, deuteron, tritium, helium-3, helium-4, etc. So these are the light particles, and except neutron, the remaining projectiles are positively charged particles. These positively charged particles are made to interact with the nucleus. The nucleus is again the positively charged particle. Between like charges, there exists electrostatic repulsive force, and how these particles can approach the nucleus, they experience electrostatic repulsive force. So, in order to make these projectiles to interact with the nucleus, we are going to increase the kinetic energy of these particles, so that with that very high kinetic energy, it can overcome the electrostatic repulsive force existing between the particle, projectile and the nucleus. So, therefore, we require high energy particle. In alpha particle experiment also, alpha particles approach the gold foil with very high kinetic energy, and in many nuclear reactions, the projectiles are made to strike the target with very high kinetic energy. Now, how to achieve the kinetic energy of the particles? How to enhance, how to increase the energy of the particles? So, in order to increase the energy of the particle, that means in order to increase the velocity, or we can say that to accelerate the particle so that the projectiles acquire sufficient amount of kinetic energy with which it can overcome the electrostatic repulsive force and it successfully interact with the nucleus. We are going to use device which is called as particle accelerator. Okay. Therefore, today we are going to discuss in detail about very important devices which we are going to use in nuclear physics. They are nothing but particle accelerators. A particle accelerator is a device used to increase the kinetic energy of electrically charged particles to sufficiently high value so that the charged particles can overcome the Coulomb repulsion of the target nuclear and induce nuclear reactions. Now, such a device is called as particle accelerator. The first particle accelerator was built by Cockcroft and White. As the classification of these particle accelerators can be classified in two different ways. They can be classified based on the shape of the path followed by the particles during the acceleration, and we can also classify the accelerators based on the method used to accelerate the particles. In first way, the accelerators are classified into linear accelerators, cyclic accelerators. These two classification is based on the shape of the path followed by the particles. Here in linear accelerators, as the name itself indicates, the path traveled by the particles during the acceleration is a straight line path. The example is Van de Graaff generator. In cyclic accelerators, as the name itself indicates that the shape of the path followed by the particle during acceleration is either circular or spiral. Okay. In some cyclic accelerators, the path is spiral. In other cyclic accelerators, the path is circular. Example, cyclotron, synchrotron, betatron, etc. Now, based on the second way, that is based on the method used to accelerate the particles, we are having different types of accelerators: direct field linear accelerators, magnetic resonance accelerators, phase stability accelerators, and accelerators which works based on the principle of alternating gradient of magnetic focusing, depending upon the method. Okay, here the method is direct method, here the method is magnetic resonance, here the phase stability concept is used, here the principle of alternating gradient of magnetic focusing concept is used in order to accelerate the particles. So this is about a brief information about the classification, and we are going to discuss three accelerators which have included in the syllabus in detail, and we are going to discuss principle, construction, working, theory of three important accelerators, particle accelerators, which are those: linear particle accelerator, or it is also called as linear accelerator, cyclotron, betatron. And in this presentation, I am going to discuss in detail about the first mentioned accelerator, which is linear accelerator, also called as linear particle accelerator, or in short form, these accelerators are also called as LINAC, L-I-N-A-C. These linear accelerators are also called in short way as LINAC. Now this LINACs we are going to discuss in detail. Linear accelerators. principle. Let us look at the principle. Linear accelerator. In linear accelerator, acceleration of charged particles is due to the electric field which is present between the gaps of adjacent tubular electrodes and having uniform velocity inside the tubular electrode with no field, which is due to the resonance of the applied field with the motion of the particles. This is a principle of linear accelerators. So we can understand this principle better after discussing the construction and working. Here you have to understand that here the particles gets accelerated because of the electric field which is present between the gaps of the electrodes, and the electric field is absent inside the electrodes. Between the electrodes there exists electric field, and inside the electrode the electric field is zero. And when the particle enters into the region in which the electric field is present, it gets accelerated, and when it enters into the region when there is no electric field, it moves with the same velocity. It will not experience any acceleration. And in order to achieve this, we have to do one arrangement. There is one condition, that is the resonance of the applied electric field, the resonance of the applied electric field with the motion of the particles should be achieved. Then only the acceleration of the charged particle is possible. So this is the principle of linear accelerators. Now let us discuss the construction of linear accelerators. Linear accelerator is used to accelerate the charged particles. You cannot use these accelerators to accelerate neutral particles. Now it can be used to accelerate only charged particles. So this device is having a vacuum tube. Consists of a vacuum. It is having a vacuum tube which consists of a series of hollow tubular electrodes. These hollow tubular electrodes are also called as drift tubes of successively increasing lengths and are connected to opposite terminals of the radio frequency oscillator. Okay. These hollow tubular electrodes change their polarities alternatively. So here the electrodes are connected to radio frequency oscillator, which is nothing but an AC electric field, AC source. And in an AC source, you know that the polarity of the electrodes will changes after every off cycle. So here these hollow tubular electrodes change their polarity alternatively, and in order to achieve the acceleration, the length of the vacuum tube the length of the electrodes should be in such a way that it satisfies the condition, and also depending upon the final kinetic energy, the length of the vacuum tube is made, and depending upon the application, we are going to design the linear accelerator which is having a certain length. Okay, and here the series of hollow tubular electrodes, at one end of the series of hollow tubular electrodes, we are having a source, and on the other end of the hollow tubular electrodes there is a target. Okay. Now you will understand the construction better when you look at the figure. The electric field exists only in the gap between the electrodes, whereas it is zero inside the electrodes. So you look at the diagram which explains the construction of the linear particle accelerators. So here, this is the vacuum tube of the linear accelerator, which consists of series of electrodes. Look at the diagram. E1, E2, E3, E4, E5. These are the electrodes which are arranged one after the other. They are not directly connected. There exists a gap between the electrodes. They are arranged in the form of a series coaxial to the vacuum tube. Okay, look at the length of the electrodes. The length of the electrodes goes on increases as you move from one electrode to next electrode. Okay. At one end of these electrodes, we are having a source, yes, and on the other end, we are having a target. The source will release the particle that has to be accelerated, and the particles are made to enter into these electrodes. And when the particle is between the gaps of the electrodes, it experiences a force due to the electric field, and when the particle is inside the electrodes, because the electric field is zero, it will not experience the force, or we say that it will not experience any acceleration. When the particle acquires sufficient amount of energy, then directly it is made to strike the target. Look at the figure. Here we are using radio frequency oscillator to develop an electric field, and here the alternate electrodes E1, E3 and E5, these electrodes together are connected to one polarity, one terminal of the RF oscillator, and the other set of alternating electrodes E2, E4, E6, they are together connected to the another terminal of the source. Therefore, when E1, E3, E5 are at negative potential, E2, E4, E6, etc. will be at positive potential. And after every half cycle, that means after every T/2 time interval, the polarities of these electrodes gets reversed. Okay, so this is the construction of linear accelerators. Now let us discuss the working of the linear accelerators. When the particle, for example, assume that we are using protons to accelerate, assume that when the proton leaves the source, let at that particular instant the first electrode is at negative potential. Then, for this electrode, the proton is positively charged particle and the electrode E1 is at negative potential. Therefore, now this potential, because of the presence of this potential, the proton gets attracted by a force which is equal to Q times the potential difference. And this force increases the kinetic energy of the particle, and the particle accelerates towards E1, and it enters the electrode. Let us say that the particle entered the enters the electrode with a velocity v1. And inside the electrode E1, since the electric field is zero, there is no further increase in the velocity of the particle. It moves with the same velocity v1 inside the electrode E1. Okay? And the frequency of the RF oscillator is adjusted in such a way that by the time when the proton just leaves the electrode E1, first electrode, then the reversal of potential takes place. As a result, now the second electrode is at negative potential and the first electrode is at positive potential. As a result, as soon as the proton enters the gap between E1 and E2, it gets pushed by E1, it gets repelled by E1 and pulled by E2, gets attracted by E2. As a result, it experiences further acceleration and it enters the electrode E2 with a greater velocity. Let us say the new velocity acquired by the proton is E2. Now this process is repeated. That means whenever the proton enters the gap, it is moving in the electric field, it acquires additional energy and therefore it moves with a greater velocity. Okay, and this is possible. The process is repeated by increasing the length of the cylinders because the velocity of the particle increases cylinder to cylinder and these particles will travel longer distance in the same time. Therefore, in order to match with the time reversal, the length of the cylinders or the electrodes are made greater from one electrode to next electrode. Okay, hence to match with the reversal time, the length of the tubes are increased. So this is a construction of, this is a working of the linear accelerators. Now let us discuss the theory. Under the heading theory, we are going to obtain an expression for the velocity gained by the charged particles, and also we are going to get an expression for the length of the electrodes. To begin with, let us assume that Q is a charge and M is the mass of the particle to be accelerated, and let V is the potential difference which is maintained between the electrodes. V is the potential difference. Q, M and V are constant. Okay, let the particle reaches the first electrode and enters the gap between E1 and E2. Just it enters the gap between E1 and E2 with the velocity v1. Then the kinetic energy of the particle is given by half m v1 square, and this energy is acquired by the particle because of the force experienced by the electric field. If V is a potential difference and Q is a charge, then the force experienced by the charged particle because of the electric field is QV. Now this force appears in the form of kinetic energy of m v1 square. Therefore, from this equation, we will be able to obtain the velocity of the particle v1, which is equal to root of 2 v divided by m. Now small letter v is used to represent the velocity, capital letter V is used to represent the potential difference. Now with this velocity, the particle enters into the gap between E1 and E2. Okay. Now as soon as the particle enters the gap between E1 and E2, now the reversal of potential takes place. As a result, the E1 is is at positive potential and E2 is at negative potential. Therefore, the particle gets attracted by the second electrode. That means it gets accelerated by the second electrode and it acquires an additional energy. Already it is having an energy of m v1 square. Now it acquires additional energy qv and it enters the second electrode with increased velocity, new velocity v2. Therefore, the new kinetic energy of the particle becomes of mv2 square, which is equal to initial energy plus the new energy. Okay. Therefore, the new velocity of the particle v2 is equal to root of 2 into 2 qv by m, which is equal to root 2 times v1. Okay. Now, in this way, the process of energy gain by an amount qv continues at each successive gap crossing. Suppose assume that the linear accelerator is having n number of such tubes. Then, when the particle enters into the first gap, it is having an energy v1. When it is entering into the second gap, it is having energy v2. Therefore, then it is reaches the nth gap. When it reaches the nth gap, then it acquires an energy n times qv, and therefore the velocity when the particle enters into the nth gap is given by n into n into 2 qv by m, which is also written as root n times 1, where n represent the gap number. N is equal to 1 for the first gap, n is equal to 2 for the second gap, etc. Okay, so this is an expression. From this expression, you can able to calculate the velocity of, let us look at the expression for the length of the tubes, electrodes or drift tubes. Let Ln denotes the length. N stand for electrode number, first electrode, second electrode, third electrode, etc. We can express the length of the electrodes in terms of the velocity and time reversal like this. So you know that length is nothing but velocity into time taken. In nth electrode, the velocity is vn and the time is t by 2. Okay, and you substitute the expression for vn and time period can be written as 1 over f. So rearrange the things, put all the constants together, and here only the variable is n. N represent the electrode number. Okay, and therefore from this expression you can see that Ln is directly proportional to root of n. The length of the drift tube is proportional to square root of the natural numbers, that is n takes values 1, 2, 3, 4, etc. This is about the theory of linear accelerators. Now let us discuss uses and limitations of linear accelerators. Uses. So these linear accelerators can be used to accelerate both positive ions and electrons up to 32 mega electron volt. Okay, now, this is very important application or use of these accelerators. By using linear accelerator, you can accelerate both types of ions, but you cannot accelerate the neutral particles. You can accelerate either positive ions or negative electrons. So here, in linear accelerators, we are not going to use magnets. Magnetic field is not required to collimate the ion beam, as we are going to see in the other electrodes. We make use of the magnetic field. So here there is no need of magnets. Radiation loss is very small. So here we are using a charged particles, and you know that when charged particles accelerate, they experience loss in energy, and that loss is called as radiation loss. And the radiation loss is very small. Comparably, the value of radiation loss is very small when it is compared with the other accelerators. Okay. The alternating voltage used can be easily step up and step down using the transformer. Now, if you want to get a particle with higher energy, you can easily increase the potential difference between the electrodes by using suitable transformers. Since only one kind of field, that is electric field, is used, it is easier and cheaper to construct. It is easier and cheaper to build. Okay, now these are the uses of linear accelerators. Let us look at the limitations. Now, if you want to get very high energy particles, the length of the machine must be very long. Therefore, now if you want to accelerate the particle to a greater kinetic energy, you have to use more number of electrodes, and which are arranged in series. As you move from one electrode to another electrode, the length of the electrodes also increases, and altogether the length of the machine will be very long. This is a very important limitation of linear accelerators. And it is very difficult to maintain vacuum in such a large chamber. Since to achieve very high kinetic energy, now we are going to increase the length. If you increase the length, now you are going to find difficulty maintaining the vacuum in the chamber. So these are the limitations. And we are left with two more accelerators, cyclotrons and betatrons, so that we are going to discuss in the next presentation, and we are going to see that how these limitations are removed in cyclotron and betatron. Okay. Now we are going to discuss the remaining accelerators in my next presentation. Thank you.